Hello everyone, welcome back to ASIB. For the last video, we talked about mole stoichiometry. If you remember what that was, that's basically finding the yield or the product of a reaction if you're given the amount of a reactant. So instead of doing moles, because we often don't know moles, we can measure something else, mass. We can often weigh something and we know how much its mass is. And we can usually also use this mass to calculate the amount of a product that we will get. This is what we call mass stoichiometry. The first thing I want to note is that you cannot directly use the mole ratio to convert mass to mass. This is because the molar mass of each element is different. Instead, we must convert the mass of the reactants into number of moles of the reactants, then use number of moles of the reactants to figure out the number of moles of the product. And only once we have that can we convert it back from moles to mass of the product. Here is an example question. The balance equation is given to us above. What mass of copper, Cu, is required to produce 150 grams of nitric oxide, NO? Well, we should first take the 150 grams of NO, 150 grams of NO, and turn that into number of moles of nitric oxide. In this case, that would be 1 mole of nitric oxide over 30.01 grams. The molar mass of nitric oxide is 30.01 grams per mole. And then, now that we have moles of nitric oxide, we can use mole stoichiometry to figure out how many moles of copper we're going to have. That's 3 moles of copper per 2 moles of nitric oxide. And now we have moles of copper, but the question isn't asking for moles, it's asking for mass. So finally, we have to do one extra step and turn this moles of copper into the mass of copper using the molar mass of copper, which is 63.55 grams per mole. You can pause the video here if you want to calculate it yourself. The answer is 477 grams of copper. Let's try another question. 1.00 grams of acetic acid, which is HCH3COO, was neutralized with sodium hydroxide, given the following equation. HCH3COO plus NaOH yields water plus NaCH3COO. First of all, you must balance the equation. The equation is technically already balanced because if you look at it, every element appears once. That's good. That means we don't have to do extra work. If we have 1.00 grams of HCH3COO, how many grams of sodium hydroxide, this one, will we need to neutralize the solution? Well, again, we should be using mass stoichiometry, which means the first step, you got it, was to convert the 1.00 grams of HCH3COO into moles. The molar mass of this compound is 60.06. So we have to multiply this by 1 over 60.06 grams in order to get moles of this compound. Then, using the balanced equation above, we can see that we need 1 mole of NaOH per 1 mole of HCH3COO. So we should multiply by 1 over 1. I know that multiplying by 1 over 1 sounds redundant because it doesn't change the answer, but it's better to write down everything as you're learning it so that when the number isn't 1, it's a lot easier for you to adapt to the situation and not forget steps. So now that we have moles of NaOH, we need mass of NaOH. The molar mass of NaOH is exactly 40 0.00 grams per mole. I'm writing it in 2 lines because I don't have space on the screen, but it's preferred to usually put it in all one line, one long line. And this should give you 0.666 grams of NaOH. That's how many grams of sodium hydroxide we would need to neutralize 1 gram of acetic acid. Now here is a question for you to try yourself. I have 500 grams of C6H12O6, and it is combusted according to this following equation. C6H12O6 is added to oxygen, which forms water and carbon dioxide. The question is, how many grams of water was produced from this reaction? Please pause the video here if you would like to try yourself. I will go over the answer in 3, 2, 1. Okay, so the first step to solving this question is to balance the equation first. We can balance it by using the numbers 1, 6, 6, and 6. Then we can use our stoichiometry skills to solve the question and get the final answer. 500 grams of C6H12O6 is combusted, and it has a molar mass of 180.18 grams. So we have to multiply by 1 mole of C6H12O6 over 180.18 grams of this element or this compound. And then to find the moles of water, we multiply by 6 moles of H2O over 1 mole of C6H12O6, and finally we multiply by the molar mass of water, which is 18.02 grams per mole. And this should give us a final answer of 300 grams of water. That's all for mass stoichiometry. However, that is not the end of stoichiometry, as you may have noticed. Now we will be talking about volume stoichiometry. Volume stoichiometry, in the current sense, mostly aims to deal with gases. An ideal gas, which means ideally we're not accounting for the misbehavior of any gases in the atmosphere or anything like that. Ideally, 1 mole of any gas is equal to 22.7 liters of gas at STP. Now, if you forgot what STP means, that's fine. I will go over it right now. STP is 273 Kelvin and 100 kilopascals. The old definition of STP uses 22.4 liters of gas. So if you see that, that's because they're still using the old numbers. The new number is 22.7. So if you see any 22.4s, note that it is the old number. Let's try a simple question first, just to get ourselves used to this conversion. A sample of oxygen takes up 5.6 liters at STP. How many moles of oxygen is there? This should be a quick and simple calculation. We take 5.6 liters of oxygen and we convert it using 1 mole of oxygen per 22.7 liters of oxygen. And the answer should be 0.25 moles of oxygen. This is how we convert volume to moles for gas at STP only. Later on, we'll be dealing with solutions, which deals with liquids and their own volumes and concentration. But for now, let's just only talk about gas. Notice that now, since we can convert liters of gas or volume of gas into the amount of moles of gas, we can also do stoichiometry now with gas. Here is a question. Nitrogen and hydrogen react according to this following equation. N2 plus H2 yields NH3. This equation needs to be balanced, but let's do that later. What volume of hydrogen is necessary to react with 5 liters of nitrogen? Assume STP, which means that we can use the 22.7 as our conversion rate. So the first thing we must do, as I said earlier, was balance the equation. We can balance it like this. N2 plus 3H2 yields 2NH3. And now we can do stoichiometry with it. We have 5 liters of N2, and we can multiply that by 1 mole of N2 over 22.7 liters of N2. And now we have moles of N2. And then we want to find volume of hydrogen, right? So we need moles of hydrogen first. 3 moles of H2 over 1 mole of N2. And then we need to multiply that by 22.7 liters per mole of H2. So that's a negative 1 there. Let me just rewrite that quickly. There you go, that's a negative 1 there. And this should be, you guessed it, 15 liters of H2. Now, you might ask me, well, we have a 22.7 here, and we have another one here. Why do we have to write the 22.7 at all? That's a good question. Because right now we're converting from gas volumes to gas volume, the 22.7 is essentially redundant. However, if you're working with a gas and something else that's not a gas, let's say a solid or liquid, then the 22.7 only goes one way, right? Only the gas uses 22.7, nothing else uses 22.7. Therefore, I would still encourage you to write it out, even though it might be redundant or cancel it out later. You can just cancel it out. Here is a question that requires you to actually use a 22.7 in only one side. Let's use the same equation as before. N2 plus 3H2 yields 2NH3. But this time, instead of giving you volume, I'm asking you what volume of NH3 at STP is produced if I have 25 grams of nitrogen. Now, in this case, you can see that we're not going to be using 22.7 for the nitrogen. We have 25.0 grams of nitrogen times 1 mole of nitrogen over 28.02 grams of nitrogen. And by the way, yes, the molar mass of nitrogen is 14.01, but we have N2 here, which means we have 2 nitrogens. So therefore, the molar mass is doubled. And we have to multiply that by 2 moles of NH3 over 1 mole of N2, which you should be familiar with by now. But at the end, notice that we want volume of NH3. And since we want volume of NH3, we must multiply by 22.7 liters per mole here, but we don't do that earlier, right? Because we had mass of N2. And this would be a situation where the 22.7 actually comes into play and is not able to be cancelled. This is why I would encourage you to write it down every time. And if it repeats itself or if it can be cancelled, just cancel it or don't take it into account. The answer is 40.5 liters of NH3. Now I would like to touch on a subject that is known as limiting and excess. So in chemistry, if you're given quantities of a reactant, there are 2 possibilities really. The first one is there are just enough of each element. So somehow you've measured them out to like the nearest 10,000th of a gram, and they run out at exactly the same time. You have that's what we've been assuming earlier. we haven't taken into account like, oh, we don't have much of the other one, or well, we only have a limited supply, right? We're assuming that everything's theoretical, we have the exact amount we need. However, this is usually not the case in the real world, right? Realistically, one will run out first. One of them will run out first. And limiting the excess aims to calculate which one will run out first, how much of the other one we'll need, and how much of the other one will be left over if one of them runs out first. Okay, so here is a limiting and excess equation, or sorry, question. Suppose we have hydrogen and chlorine, which are reacted according to the following equation. H2 plus Cl2 yields 2HCl. We have 4.50 grams of hydrogen and 140.0 grams of chlorine. The question is, how much or what is the mass of HCl that will be produced? Now notice that we have limited amounts of each reactant. So we have to calculate how much each reactant will produce and take the minimum value. Let's start with hydrogen. 4.50 grams of hydrogen, convert it according to its molar mass of 2.02 grams. And then we have to say that it's going to form 2 moles of HCl per 1 mole of H2. And then we convert it according to the mass of HCl, which is 36.46, I think. 36.46 grams of HCl per 1 mole of HCl. And the answer should be 162 grams of HCl. Sorry for running off the screen there. That should say HCl. Actually, I'll just rewrite the whole thing. 162 grams of HCl. There you go. Now that we know how many grams of HCl will be produced by the hydrogen, let's talk about the chlorine. It's a similar process. 140.0 grams of chlorine converted into mass. 70.90 grams of Cl2 forms 1 mole of Cl2. Then mole stoichiometry, 2 moles of HCl per 1 mole of Cl2. And then lastly, let's multiply it by the mass, 36.46 grams per mole. And this should give us only 144 grams of HCl. So notice how even though it seems like we have more chlorine, right? Because chlorine is so much heavier than hydrogen, that it actually ends up being the limiting reaction. So the question is, what is the mass of HCl produced? It would be 144, because I cannot have extra chlorine to react with the hydrogen, but I can have hydrogen that's left over. Now, the follow-up question to the question that we just did earlier would often be, well, how much H2 will be left over? So what mass of hydrogen is left depends on how much you actually produced, right? So in this case, we would have 162 grams the hydrogen would have produced minus 144 grams that were actually produced. And we get 18 grams of HCl that would have been theoretically produced by the hydrogen. We can take this 18 grams of HCl, multiply it by the moles. So we would have 1 mole of HCl over 36.46 grams of HCl. And then we multiply that by 2.02 grams of hydrogen. Sorry, I skipped ahead of myself. This is 1 mole of HCl. And then we would have 1 mole of H2 per 2 moles of HCl. And then we want to multiply that by 2.02 grams per mole of hydrogen. It turns out the mass of hydrogen left over is 3.98 grams of H2. And this is the amount of hydrogen that would be left over as excess after the chlorine is completely gone. In this case, we say that the chlorine is limiting at, Cl2, chlorine is limiting, and the hydrogen, the H2, is in excess. Like that. Lastly, I wanted to quickly touch on percent yield. So, up until now, we've been calculating a theoretical yield, right? What we expect to be produced. However, in the real world, we know that sometimes things are lost, right? You're not going to retain 100% of your product. There might be impurities, reactions may not all react, some of the products might be lost during procedures. For example, if there was CO2 gas, some of it might have escaped in the atmosphere, right? So in these cases, the actual yield that we measure will always be less than the theoretical yield because we are not 100% efficient as much as we try to be. The actual yield is the amount defined as the amount actually obtained in the experiment. The theoretical yield is the amount determined by stoichiometry, or the amount you should get under perfect conditions. However, no human's perfect, so we never actually get to theoretical yields. Here is an example of a percent yield question. Bromine was made according to this following equation on the screen. 10.0 grams of HBrO3 was reacted with an excess of HBr. That means HBr, there was no limit. And only 26.3 grams of Br2 was produced. The question is, what is the percentage yield of the reaction? In order to do that, we have to calculate the theoretical yield of bromine that would have been obtained. So let's do some stoichiometry. 10.0 grams of HBrO3. Divide that by the molar mass. So we have 1 mole of HBrO3 over 128.9 grams of HBrO3. And then we multiply that by the 3 moles of Br2 that we should be getting over 1 mole of HBrO3. Lastly, we multiply that by the molar mass of bromine, which is 159.8 grams per mole. Notice that this amount is doubled from the actual one listed on the periodic table because we have Br2. And this should theoretically yield us with 37.2 grams of bromine. So now we know the theoretical yield. How do we calculate percent yield? Percent yield is just actual yield over theoretical yield, right? It would make sense. It's how many percent of the theoretical yield you actually managed to obtain. So in this case, we should take 26.3 grams that was actually made, and we divide that by the theoretical yield, 37.2. And the final answer is 70.7%. You can add actual yield over theoretical yield times 100 if you want. I prefer not to, but that's completely up to you. The answer should be 70.7% regardless. Alright, that's all for this video. If you like what we do, please like and subscribe, and stay tuned for the next video, Stoichiometry Part 4.